Hello everyone, welcome to Physics 2211, Lab 3, Black Hole and Orbits. So this lab's general purpose can mainly be split into two parts. So in part one, we were to analyze the motion of the star and determine the mass of a black hole using a predetermined trajectory based off our Georgia Tech emails. And in part two, we were to find the initial velocity of a spaceship needed to achieve a figure 8 orbit influenced by a moon and a star that we would find by simulating gravitational interactions between these three objects. So some of the fundamental physics concepts that we used were mostly Newton's law of universal gravitation, which was central to this entire process, largely because we're dealing with the gravitational interaction between different objects. The momentum principle was crucial in this entire lab, specifically for modeling motion of objects in the velocity and position update formulas, which can be derived from the momentum principle, and the parallel and perpendicular components of the net force. So we have both of those here, which were used largely in the second part, when we were finding the interactions between the three objects that we were exploring. So before we go into the specific code models as a whole, we'll run through a brief description of the main results. So in part one of the lab, we are to find the estimated mass of the black hole. From my specific Georgia Tech email and my initial seed, the mass of the black hole came out to be 1.46 times 10 to the 34 kilograms. And in the second part of the lab, I found these two velocity values, the x component and y component of the velocity, which led to this pretty remarkable shape here. If we continue to run the code, the pink path will continue to the spaceship will continue to orbit around the moon as it goes around the planet. And this was mostly found through trial and error. We'll discuss all that later on. But yeah, I'm really pleased with how it came out. And yeah. So the computational model, which is part one, for part one specifically, we use the seed, so this is my Georgia Tech email, and we use these initialization values, specifically the gravitational constant and the mass of the star, and the time interval, which were both given in the lab instructions. So 86,400 is the number of seconds in one day, and we use this indexing to help model the velocity value, which we continue on here. As described previously, we used a lot of fundamental physics concepts. dp over dt was one of the main ones. And we use Newton's second law in F net equals dp over dt, so the rate of change of the momentum. And as you can see, we model parallel and perpendicular components of the net force, which helps us create a model that properly represents the black hole. So in part two is a little more complex in terms of the number of values and the different values we were working with. We have our initialization for physical constants, so we have the universal gravitational constant, which doesn't change. We have the mass of the planet and the moon and the ship, which are all provided. And delta t we keep as 60 seconds, so 1 minute. And in our while loop here, we begin by modeling the position vector from the planet to the moon and the ship to the moon. And then we continue on our calculations, especially here, where we model Newton's law of universal gravitation, which is gmm over r squared. And we times the unit vector for directional value. And yeah, you can see that the while loop allows us to properly model the trail of the ship around the moon as the moon orbits the planet. So some possible errors and things that we can discuss, especially as we potentially use these models to predict the real world, are number one, approximation of precision, which is a pretty significant issue. We can't always use these types of models, especially in the way that we did, where we were assuming the black hole or the star was the only source of gravity in the system. We cannot assume that there is no other source of gravity in nature because there's simply too many variables, especially in space, when it comes to these types of situations. Number two is accuracy. So we used a brute force approach to find the velocity values, which we don't necessarily know is the most optimal method to achieve the better orbit. And now we'll address some hypotheticals. So the first hypothetical we'll address pertains to part one. So how do the components of the net force, so the parallel and perpendicular components of that, compare to the same components of the rate of change of the momentum? So mathematically, these two are the same thing. Newton's second law states that the net force is equal to the rate of change of the momentum, so dp over dt. The process of calculating these components is quite different, and we can see that it's actually quite easier to calculate the rate of change of the momentum rather than to calculate specifically the components of the rate of change of the momentum over the components of the net force, largely because we only need the change in velocity for the calculation of the rate of change of the momentum rather than calculating the components of the net force. So how would our model change if we were to include a black hole in our system in part two? So the mass of the black hole was very large. It beat the masses of every other object in the system. So Since in this hypothetical we're putting the black hole in the system, this would create a largely dominant interaction between the black hole and the other components of the system due to the black hole's extremely large size, which would, using the universal law of gravitation, would cause multiple changes in the interactions between the black hole and the other objects, more specifically the spaceship and its motion. Thank you so much, and have a great day.